Hello everyone, good afternoon. Welcome to this proton and heavy ion session on preclinical flash in vivo. So our speaker is Brita Sørensen, who is a professor at the Danish Center for Particle Therapy at Aarhus University in Denmark, and we'll be talking about proton flash in vivo and what matters. So over to you, Brita.
Thank you so much. So I'll talk to you today about some of the proton flash experiments we're doing in Aarhus and what factors we have looked at and that is influencing the flash effect. And first, this is my conflict of interest. I'll show you data from projects which are financially supported by Varian. So first of all, since 2014, we've now seen a lot of papers showing that flash induce less damage in normal tissue at isodose with conventional radiotherapy, while the tumor response seems to be maintained. This has been shown for electrons, protons, carbon ions, and X-ray. It's been shown for a range of different endpoints, and it's been shown for different animal models. But by now, we kind of realize that this is not black and white. It's not there is a flash effect or there is no flash effect. Now we're looking at a number of different parameters which potentially may influence whether there is a flash effect and the magnitude of the flash effect we see. And these parameters are things like dose rate, time structure of the beam, could be radiation modality, could influence the flash effect we're looking at, tissue type, the dose that's given, and with that also fractionation. And we've been looking at some of these parameters in Aarhus. And the setup we're using, and this is a setup that will go through all the data I will show you that's based on this setup. So we're using mouse leg as target. We have the mice restrained in a little jig like this. We're irradiating them unanesthetized. The mice have the water bath, or the leg down in a water bath, and we're irradiating in through the water bath. And the body is shielded by brass. And then we have different dosimetry measures here also. We have alanine pellets, one per mouse in the entrance, and we have a scintillating crystal with the mouse leg to give the dosimetry. The first data I'll show you here, they are conducted with transmission flash, so shoot-through flash. And for all the studies, we're using pencil beam scanning. You can see the pattern here. We're doing one field per mouse. That's a 2 × 3 centimeter field we're using. And although you can see on the picture down in the corner, we have 3 mice at the water bath at the time. They're irradiated with one field per mouse to keep the dose rate up. And you can see the mouse leg here in the next picture underneath the water surface. So we have the endpoint we're using the most, that's normal tissue damage, so acute skin toxicity. So after radiation, we're assessing the acute skin toxicity in the targeted area on daily basis from day 11 to day 21. Then we are calculating the percentage of mice with a certain score at any time in this time interval in each dose group. And with that, we can do dose response curves of the acute skin toxicity. And the first experiments we did when we compared conventional dose rate versus flash, we used the slowest possible dose rate for the conventional we could use, so 0.4 gray per second. This was obtained by delivering the field with repainting. And the dose response curve here, we have 9 to 21 mice per dose group, so 154 mice in total. For the flash, we used a dose rate between 71 to 90.7 gray per second, and that's a field dose rate. Everything I'll be referring to here is field dose rate. This was the fastest possible dose rate we could obtain. We have in this dose response curve, we have 144 mice, 12 per dose level. And this is just for the medium skin toxicity. Then because we can score at different skin toxicities, we can obtain dose response curves here for the different skin toxicities. And then we can compare at the D50, the dose it takes for 50% of the mice to response. We can calculate the protection ratio, so the difference between the dose response curve, the ratio between the dose response curves. So we see here a flash sparing factor from 1.41 to 1.55, meaning that we need a 41 to 55% higher dose when we're using flash in order to see the same biological response. And I can also show you the dose response curves like this. So these are the same dose response curves I showed you before. I would just put all the conventional in one and all the flash in one. So you can see now clearly that the different toxicity levels, they have a different D50 for inducing the toxicity. You can also see that in flash, all the dose response curves have moved to the right. And then what we have here is like a sweet spot here around 40 gray, where we have the largest separation between the conventional and the flash response. And that prompted us to wanted to look at if we use this dose, 40 gray, and then varying the dose rate. So instead of going go for the lowest possible dose rate to the highest possible dose rate, to look at what's happening in between here. So do a dose rate response curve. So we did that like this. So this is all the mice here irradiated with 40 gray, and then we've been varying the dose rate, and the curve here are done without rescanning, and we have 6 to 25 mice per dose point. So you can see here in a medium toxicity level, the score 2.5, we have this very nice sigmoid curve displaying the dose rate response. But if we're then looking at one of the other toxicity levels, if we look here at a lower toxicity level that has a lower D50, then the dose rate response looks different. So now we need a higher dose rate in order to obtain a flash effect. If we're going to the other side and looking at toxicity where we need a higher D50, so at a higher toxicity level, then the flash or the dose response curve moves to the other side. So now we need a lower dose rate in order to see a flash response. So this is prompting us to think of that if we're using single dose points, then we can see a very varying flash effect. So whenever we are not doing dose response curves, the flash response we see is very dependent on the dose sensitivity of the endpoint we're using, as well as of the dose rate. But it becomes actually more complicated than this, because as I said to start with, when we did our first experiments, to get the conventional as slow as possible, we irradiated the mice with repainting, so that the conventional mice, the dose were delivered with repainting, and in the flash irradiated mice, the dose were delivered without repainting. And repainting just means that we are scanning with the pencil beam, we are scanning the field multiple times. For conventional, it was 320 times that the field was delivered. So we tried also to do this dose rate response curve, but with repainting, and repainting the maximum number of times we could for each dose rate, while maintaining the same field dose rate. So this is just a matter of whether the beam is moving a little bit slower or really fast multiple times. The overall field dose rate was kept constant. So this was the dose rate response curves I showed you before. And then if we are doing exactly the same, but now with repainting, you can see that for these different toxicity level, the dose rate response curves are moving toward the right. So now we need a higher dose rate in order to obtain the same flash response. So what we see here is that we don't see any apparent dose rate threshold. This is very dependent on the dose sensitivity of the endpoint we're using. We see a flash effect over the whole range that we are using. Actually, for the highest dose sensitivity, we saw a flash effect at really low dose range or dose rate. This was dependent on the dose sensitivity of the endpoint, and also that the flash effect was dependent on the time structure of the dose delivered. We were also interested to look at the impact of split dose. So this is raising the question, how will overlapping fields impact the flash effect in the normal tissue? Or if you have beam interruption while you're delivering your beam, how would that affect the flash effect? So we again used this dose of 40 gray, where we had the largest separation between flash and conventional. Now we fixed the dose rate at 60 gray per second. And then we delivered the dose either as one total dose, or we split it up in smaller deliveries with 2 minutes pauses. And the data I'll show you here, we have 13 to 21 mice per dose point. So just to start with, we tested the conventional dose rate, whether we delivered it 40 grays at once or 40 grays split into 6 different deliveries with 2 minutes pauses. We did not see any difference in the percentage of animals with toxicity. Then if we look at flash, so this is delivered in 1 time 40 gray. So this is exactly confirming what we saw before, very large separation between conventional flash. Then if we split it into 2 times 20, and this is every time with 2 minutes pauses, we see already a smaller flash effect. At 3 deliveries, we see quite a compromise of the flash effect, and this is plateaued from 4 and 6 deliveries. So we never see it reach the same level as a conventional, but it seems to plateau out after the 3 to 4 deliveries. So another question that we have right now, because everything I showed you so far, that's done with shooting through flash, so in the entrance. So another question was whether we could do spread out bragg peak flash. And Line has just showed a poster of this today, and I think you can still find the poster if you're interested in seeing the exact same setup, and now done in a spread out bragg peak. And then we were interested in looking at how proton flash compared to electron flash. So we had access to electron flash at our institution since the spring. So we have conducted the exact same setup, exact same experiments as I just showed you, but now with electron flash. Here the dose rate was 200 gray per second, and the dose range we used was 19 to 55 or 85 gray. And then we saw dose response curves like this, so very much similar to what we've seen with protons, which are lying there. So these are the protons curve now lying on top of the electron flash. So very, very similar dose response for whenever we're comparing proton flash and electron flash in the same assay and the same setup. But this was all on normal tissue. The other side of the flash story is, of course, the effect on tumors. And a paper just came out earlier this year, a systematic review of flash papers looking at tumor response. And what they found here was that there was 15 publications with 66 data sets looking at tumor response from flash radiation. And there was only one study in between here was TCD50, and I'll show you this in just 1 second. But overall, they found that the data supported that the ultra-high dose rate isoefficacy compared with conventional. But it was very highlighted from the authors here, which I agree with, that it's a limitation that most of these data sets are tumor growth assays. These have very short follow-up. So we need more experiments with TCD50, and we need various tumor models which are representing different histology and different radiobiology behavior. But I'll just show you the one TCD50 study that we did. So this is done in the exact same setup as I showed you before, mouse leg in the water bath, and now we have implanted a tumor subcutaneously on the foot, and then we can irradiate everything on the same way. And our endpoint is tumor control, so this means no recurrent tumor 90 days after treatment. And here we see the conventional dose rate or dose response curve here shown in blue, and the flash dose rate response curve in red, and we see no significant differences in the 2 dose response curves. So this is where we are so far. So most important questions from preclinical research of proton flash. Well, first of all, is there a normal tissue sparing of flash? And yes, we can see that. And yes, can we quantify it? Yes, we can, but it's extremely dependent on a number of things. It's extremely dependent on all the things we normally or would think would affect the flash effect, dose rate, and so on, but it's also very dependent on the endpoint we're using and the dose sensitivity of the endpoint. And then to the other side of the coin, is there an effect of flash on tumor response? Well, so far, all the studies have been looking at it, it does not look like there is a flash tumor effect. But the tumors I've been using, it's very experimental tumors. And we still have a lot of questions about the factors that we normally know affect radiation response clinically. These are factors like tumor hypoxia, intrinsic radiosensitivity, HPV status, and so on and so on. So I would say that the tumor response question is not out yet. There's still a lot of open questions to make sure that we will never see a flash effect on the tumor, or at least a tissue-sparing effect on the tumor. So where do we need to go from here? What can we supply from the preclinical research? What would be nice to know about flash before a clinical translation? Well, it would be very nice to know what the mechanism is, and I know there's a lot of nice presentation here with different hypotheses and validated at different levels. It would also be very nice to know how large a flash effect we can expect in different tissues. Do we need to sacrifice on conformality? I'm here thinking, or can we actually use a spread out Bragg peak? Can we fractionate when we're delivering flash? And are we sure that we never see a sparing effect in tumors? And these are nice to know questions, but I would say that need to know is at least the last three, whether we can deliver flash without sacrificing conformality, whether we can fractionate, and whether we would see a sparing effect in tumors ever. And if we need to compromise in any of these, then we need to be able to determine how large a flash effect we can see in the different tissues, so we can balance the different questions to see whether we expect an advantage of using flash or not. And with that, I would just like to thank everybody involved from my department, and thank you so much.
Thank you very much. So just a reminder, online participants, if you want to submit your questions in the Q&A chat, and in-person participants, if you'd just like to come up to the microphone to ask your questions. Yes?
Thanks for the wonderful talk. Going back to the repainting study, so you're repainting a pencil beam scanned field. Is it fair to say that both the field dose rate and the beam current were sort of held constant, yet you saw a differential flash effect?
Yeah.
Is that a fair conclusion?
Yeah, that's exactly the conclusion. So it of course comes down to that the field dose rate is not a very good measure when we are talking pencil beam scanning. So the field dose rate is the most conservative way of determining, so this is where, of determining the dose rate when we are talking a scanning beam. But there is a number of different ways that are probably more accurate. And whether using the PBS dose rate would actually catch this difference, I'm not really sure it would, but there are definitely dose rated definitions which would be closer. And that's definitely what that shows, that the field dose rate is not giving the accurate picture.
And the beam current being the same also shows that the average dose rate is not predicting the flash effect as well.
Yeah.
All right, thank you.
So that the time structure itself, gives a difference.
All right, thank you. Very interesting and very clear, as always. When you did the multiple beams experiment, you started from a dose that was high enough, that every single beam was still fairly high. Do you see, is there a reason to wonder whether this applies to situations where the total dose is lower, and so also the total dose per beam will be lower, if the question makes sense?
So are you asking about a threshold, whether we can determine a threshold dose here?
Yes.
Yeah. See, I think that's a very good question. It's very tempting for me to say that we are looking at threshold doses for this, but it's not final determined. So it looks like in our system here that as long as we're above something like 10 gray, then we see a different flash effect. But this is, when we're doing it like this is like an add-on dose. So biologically, it would not be the same to say that we have a threshold for a single delivery that would equal this. For this, we need assays with a lower dose sensitivity. And there are really no good in vivo systems with so low dose sensitivity, which is why the threshold question is so difficult to answer in vivo. And then we need to move in vitro, and it looks like in vitro we don't see the same magnitude and flash effect as we do in vivo. So it's a little bit of a catch-22 question. So I would say we would like to think it's pointing towards it, but it's not the right way to determine a threshold effect.
Thank you.
Are there any other questions? Yeah, at the back.
Thank you. It was a fantastic overview. A question is, when you see the saturation in the pulse at the radiation, no? So the reason why you see this difference, do you have any guess? And it's maybe dependent on the single fraction that you give?
Yeah. We think it may be due to how we chose our conventional, because we see when we did our dose rate experiment, we see that already in the very low end of the dose rate, we can already induce a flash effect. And our conventional is 0.4 gray per second, but if we had chosen it at 0.7 or 1 gray per second, we would probably have seen a difference in the magnitude of flash effect we see. So that both come down to that when we're comparing experimentally flash effects, the conventional is probably a very determining factor. But we think also that's why we will never get up to reaching the conventional even when we have a plateau. So there's like an inherent gap in between the effects there, but it's only speculation from our side. But I think that's what it represents.
You listed a number of things you'd like to know about flash. I wonder if one of them, because obviously all the work you've done is on the fairly acute reactions after therapy up to 21 days. What about some of the later reactions that we know can occur after therapy? Do you think we're going to have to investigate that too?
Yeah, I didn't show it here today, but we have on the same animals, we also have late effects on some of them. And what we see and what we already published is that in the data we have, it looked like the flash effect on fibrosis, which is the late endpoint we have here, is not as large as what we see from acute. But we don't have a lot of animals yet to show that. It's one of the things we're working on because we need quite high doses. When we're doing flash, we need really high doses to induce fibrosis in our mouse legs. But in the sparse data we have, it looks like we see a smaller flash effect when we're moving to the late reacting tissue compared to what we see in our acute reacting tissue.
Thank you.
Yeah.
Are there any other questions? So just coming back to your final point about not necessarily needing to know the level of flash sparing in different tissue types, how would you sort of, in your opinion, how do you think that should be handled in treatment planning? Do you think we should apply any kind of like RBE style sparing factor, or should we just assume no sparing and then?
Yeah, see, that's a very, very good question that I hope other people than me will answer. I don't know. I think that your RBE idea just points to that right now we have a big RBE confusion anyway, so maybe that would not be the best way to do it. But we would need to know at least, unless we can just do as we do today and fractionate as we normally do and give beams as we normally do and say, hey, now we do it at flash dose rate. If we win anything, it's good, but we're not losing anything. But probably will come down to that we need to do less fractionation, we need to do fewer beam configurations. So we are losing something, we are compromising something. And to then be sure that we're gaining more than we're losing, then we need to know the magnitude of the flash effect in the different tissues. So I think from the preclinical side, we still have a lot of work that we can supply here.
Great, thank you. So if there aren't any more questions, then let's thank our speaker one last time. We'll close this session. Thank you.